Hi everyone, and welcome to today's session. Today we'll be touching on quite an interesting paper called MemOS. Basically, in the past, large language models have their own internal memory, like for example, the weights and biases, otherwise known as parameters. Also, some people have infused it with external databases or knowledge graphs, and those are called external memory. And typically it's been done quite separately. Like the LLM will be trained first, the external memory will be provided separately. And some people even have an in-between state where basically they store the external memory as key value pairs. Okay, so that you don't have to recompute from the input tokens to the key value layer. You could just store the key value layer and just put it back into the equation. So that is actually in this paper known as activation memory. So what's unique about this paper is that, this traditional three states of memory usually are separate, right? But this paper unifies them together into one framework called the MemCube or memory cube. And you can just transition between these three layers, like depending on the frequency of use. So I quite like this idea. I mean, it's something like, your hippocampus stores the memory, and then if it's stored more in a long-term fashion, it goes to the neocortex. Yeah, so if it wants to be used more rapidly, maybe it will be encoded in muscle memory or something like that. Yeah, so there's quite some analogy to human memory here, um, at least the body-based memory. Yeah, so this is an interesting paper. And beyond that, they propose, like, if this is the MemCube, the rest of the architecture is like this big, it's like very huge after MemCube, because the MemCube is just a unit of memory. And after that, you can subject it to many, many forms of memory manipulation. Okay, to be honest, this is way beyond like what we have right now. It's a bit hard to imagine, but I guess once we investigate further into how to make memory be something like a system program that can be manipulated by other programs, once you explore this paradigm more, it gets more and more familiar. Okay, right now, even for me, it's something quite foreign, because when we talk about memory, I always think of static memory and memory that's stored in the language model, memory that's stored in the database. If you think of this memory as being able to be manipulated by many, many other programs, or even other programs, other LLMs maybe, yeah, that's quite interesting. You can even have an ecosystem of people manipulating each other's memories. Yeah, so that's an exciting future to have. So without further ado, let's begin. So this is the traditional way of doing memory in large language models. So if you take a look over here, this is like how we normally do our prompting. We have a system prompt here, like we can just say, like, you are a friendly assistant. Yeah. Then your user query might be like, find me books about memory. Okay, then basically what will happen is that you go through your database, and then based on, maybe you have a tool use, you can query books about memory. And in your database, you encode this into some embedding space. So your embedding space will be like this. If this is a XY axis, you use TSNE or some dimensional reduction. You bring down your embedding space into 2 dimensions. Maybe books about memories here. And then, your books itself are these circle points here. And then this circle might refer to, okay, this circle here might refer to stuff like, book 1. This circle here refers to stuff like book 2. This book 3. So all these books have some things about memory in them. Okay, while the books that are further away, maybe these books are more like, this one is maybe about holiday, it's not a memory book. But based on embedding space, if you embed like the chunks of your books properly, the cosine similarity should be very, very close to your query. And so you can take maybe the top K chunks, in this case, top 3 chunks, you augment it with the 3 books here. So maybe your book 1 chunk will be like, memory is found in the hippocampus. Your book 2 will be, memory is stored in hard drive computers. And then your book 3 chunk might be, memory is stored in the interface between I mean, it's stored in the interface between the user and the robot or something like that, or something like that. That is I mean, different kinds of memory definitions. There's so many things about memory out there. So you can perhaps, put in this tree, and then the large language model will take in this prompt, this user prompt, this chunks here. This is typically known as a retrieval augmented generation. So this one, you just put into the context of the large language model. And out comes the response to the user. So the response to the user might be, like based on your query, I recommend 3 books. And then like the summary is as follows. Yeah, something like that. So this is how a typical memory retrieval is done. Without the external database, you may not have the up-to-date context about the books. Okay, and without the LLM, you cannot like digest it into a nice familiar response to the user based on a system prompt. Like you can even say like give citations and so on, and then the output would contain the citations. Whether it's accurate or not is another issue, but this is traditionally how things are done. Yes, Derek, you wanted to say something? Oh, all good.
Yeah, all good. I think Andy Sim might have the microphone on. I'm not sure if they need to say anything though.
Oh, sorry, is it me? Okay, let me turn it.
No worries. Okay, if you have anything, just feel free to let me know anytime. All right, so this is how it's done right now. And how MemOS tries to do it is quite different. It's quite different. So let us go through some fundamentals first before we go into how this is done in MemOS. So this is their previous paper, MemCube. Actually, it's also called MemCube. They like the name MemCube a lot. Yeah, so basically they have characterized using some complicated math equations. Transformers can be split, their knowledge base of the parameters can be split into abstract and specific. Basically, specific is like something like it can form a graph based on the input tokens. Abstract means it cannot form the graph. Okay. I don't think the math is that important, but basically the idea is that, you could have specific domain knowledge about certain topics, and then this abstract knowledge is like more like a general knowledge kind of thing, right? The math equations for all this, I mean, it's just for formality. I think in general, people can accept that there's abstract knowledge, which is like applies to all kind of things, and specific knowledge, which is like separated to domain. All right. So in this separate knowledge, they even split into more things like implicit memory, explicit memory, and external information. So like implicit memory is basically stuff that is already in the parameters of the large language models, like your weights and biases inside your language models might already contain information about that topic. Like for example, if you ask, how do I code in Python? Chances are your large language model, having been trained on GitHub code, would already know how to code something, right? But it may not be up to date. So how do you cure that? How do you solve that? So you have external information like this. You can give it like like what we did for RAG earlier. We can give it external knowledge. Okay, that is more up to date. Right? We can do that. Actually, a lot of memory papers focus on using external information to augment what the large language model has. And I think that's a great approach. However, that is not a long-term solution, because if you keep doing this, but your weights and biases that are implicit to the LLM are kind of different, like they're singing different tunes. Like for example, the implicit memory can say the house is blue, and your external memory can say the house is green. How? There's a paper that actually studied this, that says that if you do some form of like, okay, so not exactly this phenomena, but like if you do post-training on knowledge that is different from your pre-training knowledge, you end up with like very uncertain token predictions, which is understandable because like majority of your time is spent on pre-training. You would think the house is blue, suddenly give it new data that house is green, it will cause confusion, right? So similarly, if you give external information to your large language model that is inconsistent with the implicit memory, you might cause confusion as well. Because like the LLM would be like, should I follow what I've been pre-trained on? Like, I mean, it doesn't really ask itself this question, but the token probabilities would show it. Like, there's a high probability for tokens that is present in the pre-training sequence. Then if you give it external memory, it's like, this is different. Should I follow the external memory or not? So a lot of times when you do prompt engineering, we need to we need to be as consistent as possible to how the implicit memory is structured, right? This is how I program my LLM parsing frameworks like straight JSON and parse YAML. I try to be as similar as the output structure that is expected, like be it JSON or YAML. I try to make it such that it would possibly have been encountered in their training data, right? So that it's easier to prompt. Right? If you give it something totally different, there's confusion here. So you know the traditional bias of internal memory of LLMs and external memory interfacing. That is good to update your external database very frequently and regularly. But in terms of updating the language model itself, it's kind of neglected there, because if you don't update your language model, it can cause what I said now. It can cause confusion into what is the represented data. All right. So what this MemCube paper tried to do is they tried to use this explicit memory, which is like an in between your information and the implicit memory. As what I mentioned earlier, this explicit memory is actually your key value cache, right? Which basically says that, if let's say I have my input tokens here, this is my LM input tokens. Okay, this is the input. You go through the embedding layer. So actually there will be a multi-head attention somewhere. You will have a key value. Okay, multi-head attention will give you key and value. And there's one last thing, but basically the idea is you have key and value here that is converted to an embedding vector. And instead of just discarding this key and value embedding vector, what I can do is for all layers of multi-head attention, or attention if you don't use multi-head, store the KV cache of the input tokens that correspond to external memory, right? So basically what this does is that if you already store the intermediate KV values here, perhaps what this is done is that, we can immediately put these KV values inside your LLM inside your LLM attention function. Okay, so you don't have to like retrieve from this database here directly. Basically, you retrieve the KV cache. Right, so this is a different kind of paradigm here. This paradigm assumes that you can have access to the attention mechanism of the large language model, which kind of means that all closed source LLMs, you probably can't do this because you need to directly control the model itself. Maybe a PyTorch model, you can put in these KV values in the attention computation, then you can do this. If not, what we are left with is we have to modify the input tokens here by using rec to put in the chunks as the input. But if you have access to the model, you could potentially use this explicit memory thing to try to nuance the model's output as though as it has seen that source in the input token. So it's much faster because, when you do this KV thing, it doesn't consume input tokens at all. You just put in extra parameters in the KV values when you calculate. I'll show you the equation later. So this is really interesting because what this means is that it can access troves of knowledge very, very quickly. All right, you don't have to put it in the input space. You can just put it directly in the activation space, right, or your attention space. So this explicit memory is one way to like mitigate some form of bias, but there's still bias here because you haven't changed the model's internal memory at all. Okay, this is like just instead of putting the external memory at the input layer, you just put it at the abstraction layer. It's just a change in the way that you enter the information inside the inside the transformer itself. But the transformer's base weights and biases are not altered. Okay, so there's this dotted line here. Okay, this dotted line means that, that's why I say here, most memories are already hard-coded into the parameters of the LM. For external information, there's very little learning because this line here dotted means that, you might actually put it inside the LM in some way, be it using the input tokens or be it the activation cache. But it doesn't change the base parameters unless you do some form of post-training. You do some form of fine-tuning to change the model parameters. So typically in most LM cases, we don't change the base model, all right? Because, it can be hard to change it. Okay? Unless you do your own fine-tuning, you store the model. Normally when I recommend people to use commercial LLMs, like the closed source ones, I recommend them not to fine-tune because maybe 2-3 months later, a better model will come out, then you waste your fine-tuning, right? But I think increasingly we need to come to an understanding that, maybe if you can do your own model itself, it would be much better if you have very, very skewed domain knowledge that is not present in the training data of this LM. you might be better off having your own trained language model, and that's when the fine tuning is. But better off you can do the pre-training yourself. Yeah. So this is, I mean, this idea of using the external memory to train the model parameters is not new. Okay. But this paper, when they do this MemCube paper or this MemOS paper, they have a whole mechanism of how to put this directly in the model training and the memory processing. So it's quite interesting. So let's hold that suspense for a while. So any questions so far in terms of this things here? Implicit memory, external information. I think these more or less the three main things in MemOS. Any questions? Oh, okay, all good. That's great. So this is in the paper MemoryCube, and they say that for LLMs to humans, how they compare is that if you just use LLMs without this kind of explicit memory like the KV cache and so on, it's as though you are learning with patients with impaired explicit memory, which means that they cannot store knowledge like semantic knowledge, like basically facts. You probably cannot store like autobiographical memories and so on. So I think this research is a little memory research in humans is still not the best yet, because we haven't really identified where is memory stored. We know it's stored in some regions, we don't know how it's stored. Okay, people say that yes, memory may be stored in the activations of your neural networks in some network, but we haven't really isolated a key mechanism of how memory is stored. So, using human biology to try to decipher memory, I think may be a little incorrect, because my kind of new knowledge that I've gained is that there are certain kinds of memory that may not even be stored in the brain. People might have memory stored in the body, might be out of body and so on. But let's just assume for the purposes of today's discussion that all memory is stored in the brain, right? Then yes, okay, if you don't have like stuff like explicit memory, maybe you are just learning through repetition, right? So it is like, learning. There's this patient called Henry Molaison, HM, if you can look at the literature. He basically doesn't have his hippocampus, and he can learn how to do stuff like star tracing, like tracing a star with a mirror. And although he has no recollection of doing the tracing, it takes him, after a while, he gets better and better at the task. Okay. Initially, yes, if people have recollection of this, maybe they can, through some explicit memory already know, okay, I need to do a straight line like that. It's easier. Maybe you can learn this task faster. Okay. But without such explicit memory, like semantic knowledge and so on, you might still be able to learn the task. It's just that you might take more instances, more trials in order to learn it. And so this is what the paper meant. Without explicit memory, like maybe KV caching of useful references for a certain kind of input token sequence. Like if you don't have that kind of explicit memory stored, or if you don't do rec, it might actually be slow, okay, because the LM might take quite a while before it sinks in to its main knowledge. So actually, I have a paper called Learning Fast and Slow. I also realized this. So in Learning Fast and Slow, I have a neural network memory, and I have an external memory. And it is true, the neural network memory is slow to learn. Okay, it's very slow to learn, because imagine if you want to change some weights and biases here, you need to train it over multiple epochs. You need to keep fine-tuning your neural network in order for it to show the new relation. Okay, because backpropagation takes some time to learn. Whereas if you change external memory, it is instant. Okay, you instantly change instant change. This one is slow change. Okay, but eventually, I think we need both kind of mechanisms, because even if you change your external memory fast, okay, you don't want to have a sort of this. You don't have a sort of discrepancy between your neural network and external memory, because people have done studies on it. It can lead to hallucinations, inconsistency. Sometimes it chooses one over the other. That's not what you want. Eventually, you want this kind of external memory to still be distilled back into the neural network memory. Okay, but what kind of memory should you distill into your neural network? That is the source of discussion. And actually, this MemOS paper did give a very, very nice metric to decide what external memory should be train as neural network memory, as internal memory or implicit memory of the neural network. So that's a very nice approach that they use, and I'll highlight this later. So basically, what this slide is supposed to tell you is that instead of just learning weights and biases, learning some form of external memory is important. It's important for more efficient training of your large language models. And I move on to the next slide. So this is again in the MemCube paper, which is like the precursor to MemOS. So they did a kind of mathematical analysis to see how much read and write costs, okay, do you need if you use various kinds of memory. So like, for example, if your memory is more and more used, okay, this expected usage count, all right, here they did with the 2.4 billion model, okay, and what they do is that they count the number of times you read and write a particular memory. Okay, if let's say you use it a lot, all right, your cost is very high. So if you just use rec only, basically you need to keep retrieving the memory every time you want to use it. Okay, versus if you store in like a KB cache, all right, you actually, once you store in the KB cache, you don't have to retrieve anymore. All right, your read and write cost is reduced, because instead of doing, like, for example, if your input paragraph is like 500 words, or your reference paragraph is 500 words, and if you can distill down into a KB cache, maybe you only put like 2 time instances or 1 time instances of KB values. It is actually, in terms of read and write cost, is much cheaper. Okay, because like if you do 500 words, that's like, that's like 500 time instances. Yeah. So if you do a KB cache, you can actually, based on your input, let's say this is your input tokens. Based on your input tokens, you can go through the embedding, and then like, because this is the embedding is done like per time step, and you could eventually get a lot of embeddings. So this is the embedding layer. This is the input layer. Of course, for simplicity, I only show one embedding layer. In actual fact, for transformers, you have multiple embedding layers, because every multi-head attention you have embeddings. All right. So maybe you just only store this one, this last embedding, or like the last two, to give it context of the entire passage. So every time when you do this, you don't retrieve that much. Okay, at least this is my understanding of the paper. To be honest, the paper is not very well written. It's very hard to understand. So this is my understanding of it. If the authors look at this video and think that I explained wrongly, please let me know so I can correct it. So this is my understanding. If you store in the KV cache, you don't need to store every single embedding of each word. You just need to store the last embedding or last few embeddings. Your cost of write and read is much, much lesser compared to just using native or naive rec, where you put in the whole information. Okay, of course, the holy grail is if you put in the model parameters. All right, if you just put directly in the model parameters, the cost of read and write is constant because it's already in the model knowledge. You have no need to do rec at all. You just ask the question, what is memory? And then out comes the answer based on the weights and biases of your network. So your read and write cost is constant. So of course, if you use the memory a lot, it makes sense to put it in the base memory, right? You don't have to reference any rec at all. You just answer this. So this is the cost-benefit analysis of using various forms of memory. Rec, very fast to change, very high cost if you keep using it. KV cache or explicit memory, a little slower to change because you still need to learn the embeddings, but lower cost, much lower cost than using rec. Okay, especially if you use it more, you should use this. And finally, if you just use the model itself, the weights and biases of the LLM, you incur linear costs, okay, because there's no external reference needed, right? So what this means is that this actually kind of forms the backbone for MemOS, all right? Memories that you use frequently should be stored in the parameters. Memories that you use less frequently or seldom use should be stored in rec, all right, in external databases. That makes a lot of sense, because if you don't use that memory, why put it inside your base model, right? You will just corrupt your base model's knowledge. You just reference it when you need. But if you use that memory a lot, then it should go into model parameters. And if you use it okay, let a word between frequently and seldom, maybe use it occasionally, or use it enough, all right? Use it normally maybe. Yeah, so in between, all right, if you use it a little bit more than your seldom use, then it makes sense to store things in your explicit memory, which is your activation values of the embedding spaces. And over here, I'd like to highlight that the authors tried at first, okay, to store the entire embedding values. Alright, they store the entire KV values for all layers of the transformers, and they realized that because you see this is the transformer model, right? 2.4 billion. All right, they kind of realized that storing the KV cache itself is very expensive. They don't have enough space to store this. You know, imagine your LLM, you load it, you need 1 GPU already. Then imagine every KV cache you store, you need 1 GPU to store it. Yeah. So what they did is that they actually sparsify it. They only take the embedding spaces that maybe have a certain magnitude. They store those in a sparse embedding way so that, you know, sparse embedding, what it means is that, let's say if you have an embedding that's like this. Okay, I'm just giving it a simplicity. So what you can do is you can, instead of storing it like that, you can just store like index 0, index 1, 2, 3, index 4, 5, 6. So it's one way of doing sparse embedding. Like instead of storing it in the original vector space, you just store like what is ones, what are the ones. This is one example. There are more efficient ways of doing this, but the idea is that if you have many outputs that are potentially not useful, like 0 outputs, you can kind of ignore them and you just store the stuff that are those with magnitude 1 per se. Yeah, so this is an example of sparse encoding. And if you do sparse encoding, they found that it saves quite a lot of space. I can't remember how much space it saves, but the idea is you can store like all your input references in this kind of sparse encoding way. And you don't have to recompute the KV representation again from the base tokens, which saves a lot of time because, you know, instead of 500 tokens, maybe 500 words, you can just use the KV cache, right? And you can store this KV cache across all layers of transformers. And they did some studies and they showed that, you know, like for references, let me just delete the whole thing. For references, you don't need earlier context. Okay, because when you do LM, like embedding memory, the embedding is actually based on every single token before your embedding. So like, for example, if this is your input space, your embedding for the later tokens here, for the input tokens, when it goes to embedding space, the embedding for the later tokens actually depend on the earlier tokens. Okay, so especially when you do causal embedding, you only allow the embeddings to come from, like, you only allow the influence to come from the earlier tokens. That's a causal transformer, all right? So if you actually do this kind of embedding, which is done very commonly in most LMs like GPTs, I think OpenAI, Google and Claude probably use the same as well. You actually will be influenced by, let's say this is your context. And you know, this is your reference. You'll be influenced by the earlier context when you encode your reference, because by the nature of transformers, you actually learn, your embeddings will be influenced by the earlier input tokens. Okay, this is well studied. And what they found out is that, you know, if we just ignore all this context and we just encode the reference, you lose very little in terms of accuracy. Okay, you can just encode the reference as though the reference was the only thing at the beginning. So basically, instead of encoding like earlier context and so on, so earlier context encoding reference, you can look at this paper called Memorizing Transformers. They did this. So they managed to memorize lots of math equations like this in a long PDF document, right? But if you were to encode your references directly here, and this is your input space, essentially you don't have to use like external context to do the embeddings. You can just take the input document here and encode it directly with token 0 as the start of the reference. So you know, you could store your embeddings here just using the reference without any context. And yeah, basically what you store is, after you finish it, you store this KV value as your KV cache. Right? So at least this is what I think they did in the paper. Again, I said the paper is not very well written. It's very hard to understand this paper because they use a lot of math to illustrate the concept that I thought was pretty straightforward to illustrate if you just talked about it like how I did it here. Right? So this is the kind of thing that like they found out that, you could actually store whatever you frequently use from rack, you could store it in explicit memory and you can achieve similar performance. In fact, they achieve slightly better performance, right? So this is the finding from the MemCube paper. Okay, pause here for a while. Any questions? No, that's great. Okay, I like it. I like it. I mean, at least I hope you all understand because this is the key concept of MemCube. All good, right? Maybe you give me a thumbs up if you understand what I said. Okay, great. All right. All right, so this is the math. Okay, I hope it doesn't scare people off because the paper has like 100 times more math than this. I just picked one of the easiest equations in the paper, right? So in this explicit memory, right, is a subset of the attention key values from a subset of attention heads when encoding a reference, right? Notice that they say subset. But to be honest, I also don't know how they got the subset. Okay, so maybe it's by magnitude or something. Yeah, sparse encoding, right? Yep. So during inference, the LM can directly read the retrieve explicit memories through its self-attention layers by concatenating them with the usual context key values. Okay, so this is very important, right? So for every head at layer L, okay, if let's say you want to concatenate this, okay, then the output for the self-attention layer will be as follows, all right? So the initial one, this KJ, VJ is extra, right? Extra stuff. So let me see. This is the usual equations, okay? This is the usual key value, and then this is the query. Sorry, key query value. All right. So KQV, right? This is how you do the self-attention. Like for example, you do the query concatenate with. Oh, sorry. This Q is the query. Let me erase this. So you have a query you want to ask, like what is memory, and then you look through your values to see whether any of them match that, or look through your keys to see whether any of them match the query. And then the higher the match, the more weight you give to the value. So this is QKV, query key value, self-attention mechanism for a transformer. So how do we differ if we do explicit memory? All right. So you see here, the query did not change, okay? Because if you ask the query token is like, what is memory, like the, okay, in fact, it's not like that. Okay, in transformer, the query is actually a token, right? So you ask maybe like a query token is like memory. And then like when you query with the updated explicit memory inside, you don't need to change the query, you see, because the query is the same. It's just that instead of relying only on your internal parameters, which is in this case over here, kj is your internal parameters, right? So let me see. Each kj, vj denotes k and values of an external memory. Okay, so this is my understanding. So you see the paper is not very well written, okay? Because if you look here, down here put kj, vj, but there's no j inside here, right? So, this is the tokens that are explicit memory, right? Which is the stored key value pairs. And over here, this is the internal memory. So, I mean, the equation looks very complicated. Actually, what it's doing is very simple. In fact, I don't even think you need to write like that. But this is good for math. Except I no idea why, maybe the J is come at the bottom part. But my understanding is that when you query, instead of just using your internal memory, you also give it the KV cache of the earlier reference. So essentially, you are giving it the reference here. This is the reference part, the KV cache for your reference, and then this is your KV cache for the tokens, input tokens. Yeah, so essentially you are augmenting your context with your reference, as though as you have the words from your reference earlier on. It's just that instead of just doing it from the input layer, you do it in the embedding layer. You just put the embedding tokens for your explicit memory here. And you can put more than one source. So maybe this is source 0, source 1, source 2, source 3, source 4. So you can embed the KV cache of multiple relevant sources inside the attention mechanism. So as you saw in the earlier graph, it leads to faster memory retrieval because instead of like 500 tokens for input source, you only store 1 or 2 embedding layers. All right. So this is how the math is done. And yeah, congratulations, you've been through the hardest part of the math here. All right. So yeah, the rest of the paper is harder. If you're interested, feel free to read this paper. It's like, I think 40, 50 pages of this kind of math. Yeah. So good luck. All right. So next we move on. Why memory as an OS? Oh yeah, Derek, yeah, you want to ask something?
Yeah, I apologize. Just for the earlier slide, just one before, for the math. So you did a good job explaining the mechanism of the KV and the reference. So from my understanding, they do the sparse KV, and that's the reference, and they do that compression that you showed earlier. And then they use that to feed into the actual input tokens and then do the run the neural inference. So my concern is on the sparse compression. Do they have in the paper? I didn't get to finish it, obviously. Later on in the paper, do they have a mechanism or something they use for dealing with compression loss and data loss during the KV compression? Or do they not run into that issue because of the reference context relationship?
So I did not see anything to do with like regaining back whatever that's compressed. So for them, after compressing, it's already compressed, and you use that compressed kind of representation for all your calculations later on. And they showed that you achieve very close to state of the art, or in fact better, slightly better state of the art by doing this compression. So basically they showed that that you don't have to encode stuff in the input layer. You can encode in the embeddings and it can still work. So that's their whole paper for MemCube. So there's no mechanism to regain back the compression loss.
Gotcha. Okay. No, you're right. So the whole point was that the compression is lost. The performance is lossless, therefore the compression is irrelevant. Okay. Sorry about that. Appreciate it.
Yeah, no problem. Yeah, so this is the kind of things that like that's why I say this could be explained in a much easier way. In fact, they give me this math here. They should just draw some diagrams about the input to embedding. It's much easier to understand, but there's none of it in this paper. It's just math. So so yeah, unfortunately that's how most researchers write their papers. So you have to understand the math to understand the paper. Yeah, but that's why I'm here. You see, like I understand this, so I try to dissect it down. Yeah. So this is something that I feel has some potential, because indeed when we come to long context, every token counts, right? So if we can save some context by encoding the reference in the embedding space, sure, why not, right? Why not do that? And there's also an added benefit. You can use this to kind of do the training of your actual neural network weights also. If you unfreeze the model, you can train the weights with this embedding space. It actually can train faster, if I remember correctly. Okay, but basically this is an intermediary form that can be used to train your actual weights and biases of the original LM as well. Okay, so this is okay. Now let's move on to why is there a need for a new memory. All right, so all this whole period I've been talking about the different kinds of memory. If you remember correctly, internal memory of your LM, which is weights and bias, or in this paper they call it parameter memory. The KV cache memory of your LM, which is the parameter, which is activation memory. And finally, we have the external memory, which is like you take your sources from the database. Those sources, they form the kind of external memory. I can't remember what word they use. Plain text memory. Yes, they form the plain text memory. So why can't we just use plain text memory and LMs? Why can't we just do the default rack, right? So this is something that I'm very interested in, because I want to do fast learning and adaptable agents. If you just freeze the LM weights and biases, and you freeze your rack, okay, freeze your external data source. Okay, technically you don't freeze the external data source, but for most enterprise solutions, you don't actually change your rack a lot. You just take the rack as is. Like you throw the web one time and all the chunks from the web is stored in this external memory. You don't actually like change this memory when you do different tasks. Like for example, you ask the agent to click on a website to book a flight. And if let's say the agent realizes the website cannot be accessed through the main page, you need to go to the side page. So this very specific memory is typically not stored in the main database again. Like it will probably need to redo its actions and figure out again the next time it does it. Okay, of course, some agentic applications, they have a local memory that, stores all this details about more efficient actions. But typically, for the most part, the rack memory or the database memory is not changed. So we end up with a very static memory kind of thing. LM weights and biases are not changed. External memory is typically not changed. But if let's say you have changing situations, like your web page suddenly is down, you need to go somewhere else to access it. Or, if let's say suddenly the meaning of the word like memory is changed, and I don't want to use back the old meaning, I want to use a new meaning. Yeah. Instead of memory as a LM, I use memory as a OS, maybe that's an example. So you don't update this at all in the LM, neither do you update in the database. But it kind of affects how you adapt to the situation. Because like for us, when we see a new path, like for example, you walk two paths, one path is blocked by a stone or something, you already know, okay, next time, this path is out, we should just use this path. Right? But for LM and with external memory, agentic implementation, sometimes you may not store this kind of information. And you just keep repeating this. Then this one cannot, so I try another action. Yeah. So in order to have fast learning and adaptable agents or entities, okay, we may not want to call it agents because agents very bloated a word. We call it self-adapting individuals, maybe. Yeah. So if you want to do that, you need to update your memory dynamically. You need to be able to, retain what you need. You don't retain everything you see. Compress your memory. Maybe compress could be in the form of a reflection. You can reflect what is good, what is bad. Okay, in fact, for this is a huge research as well, because if you just ask LM to compress or reflect, it can get quite bad compression. You need to compress with a schema, something to guide it, right? Some memories are not useful, so you should discard them and prioritize. So this is also a huge form of research. How to prioritize? I would say that you need some form of emotions to guide it. Okay, so of course, emotion is not part of the paper, but this is what I think memory is used in my own understanding of memory. Memories are primed a lot with emotions, and that they help us prioritize what is an important memory. Like the more traumatic or more significant valence memory, the higher the chance of retrieval. All right, that's why people can get into depression. You see, like you keep triggering negative feelings, right? So this is something that needs to be in the system so that it can learn fast. And this is something we are moving towards. Okay, we are not there yet. Memory research is still huge, and we have not solved this problem. All right. So what this paper MemOS does is to highlight something quite important, is that instead of relying on external database and internal LM memory, why not, store it within the whole model processing pipeline, the input retrieval pipeline, doing the task, you update your memory pipeline, you store this memory as a adaptable, editable unit rather than making it static like how we do it right now. So it's a very important transition. There's a transition that will take a while because we are very used to the rack paradigm. In order to move to this paradigm, we need to kind of discard the idea that everything is fixed, which can be quite hard to discard. Okay, especially right now when we use closed source APIs, everything is kind of fixed. So we need to move beyond that if we want to do adaptable learning. All right. So overview of MemOS, I think I sort of talked a lot about it already. So let me just give you the formal definition in the paper. It treats memory as a manageable system resource in an operating system. It unifies the representation, scheduling, and evolution of the plaintext memory, which is the external memory, activation-based memory, which is like your explicit memory, and parameter level memories, which is the implicit memory, enabling cost-efficient storage and retrieval, right? And the base unit that they do this is called the MemCube. I'll be spending some time talking about MemCube because it contains everything, all three components here: plaintext, activation, parameter level. And it also contains, your memory content, metadata. And the amazing thing is that, you can use this MemCube, add on additional software layers or programmable layers to help to compose memory together, migrate memory from frequently used to not so frequently used, or not so frequently used to frequently used, combine memories together, as in compose here is like two side by side. Fuse maybe like you take 5 observations and then you fuse into one because it's the same observation, right? Flexible transitions between memory types. This is very key, all right? I've never seen this before actually. Like normally when people talk about KV cache, implicit memory and explicit memory, they typically talk about separate memory systems. Here, what this paper is proposing is that everything can be shifted from one to another. And that is amazing. That's like, it was mind-blowing, right? For me, it's mind-blowing because I've never thought of memory. I mean, I've thought of memory that can be shifted, but I thought that you need to, use some form of external structure to, perhaps shift it. Here, you shift it natively using the MemCube. Okay, so this is really cool, right? How does it do it, right? So yeah, before we move into how it does pretty well on this benchmark called LOCOMO, which is like a long-range conversation. If I'm not wrong, I went to search the LOCOMO website because the reference of LOCOMO was not given in the paper. All right, so that's why I say the paper is not that well written. Like there are some things that are hard to understand. All right, so but the idea is nice. Right? The idea is nice. That's why I spent some time looking at it. All right, so the long-term conversations is here. 300 turns, 9K tokens on average. All right, and what this means is that um, I guess you can take 9K tokens. I'm not sure whether it's 9K over 35 sessions, but you can just times 35, I guess. So it's maybe 10K times 35, maybe 350K tokens. If we take yeah, I'm not too sure whether it's 9K for all 35 or 9K per session, but let's say it's about 10K and 35 sessions. That's 350K tokens, which is a huge data set, all right? That's like 100, 200 PDF pages worth of conversations. And I'm not too sure whether Gemini 1 mil context can outbid this benchmark because it's not shown, right? But definitely for the lower context models, if your context is long, like for example, use Claude Code, right? You realize if your code base is too big, you get nonsense generation because you may not get the stuff you need. The retrieval is not that great. But if you use their system, it kind of seems to do better than like all other stuff, like including the quite popular Mem0 that has adaptable memory. Yep, it does better than any of them, and that's quite interesting. Of course, over here I didn't really like this because LLM judge is biased. So if they output in the format of the LLM's judge preference, they might get a higher score by default, even though the answer is wrong. Yeah. So um, this is not a conclusive benchmark because LLM as a judge is not the best way to judge. But let's forget about that for the moment. We assume LLM judge is accurate and fair and everything. And this is quite a good paper. I mean, like their system itself manages to retain very long context. Right? So how does this work? How does the MemCube work? All right. I realize actually it's a few more slides, but let me just go to how does the MemCube work before we go through the rest. How does the MemCube work? Okay, the MemCube works by having different kinds of memories, like for example, plain text memory, which is for example, the text itself from the source. You also have the activation memory, like for example, you want to have an activation injected at layer 12, and this is your tensor for your activation memory. So I guess they have the key and value cache here. Over here, they only show one tensor, but you need two tensors. You need the key and value tensor unless both are the same, all right? And you have the parametric patch, which is interesting. They use LoRa patch, all right? So for those who don't know, LoRa is like you have an input layer you have a layer one for your LM. Okay, maybe it's layer N, doesn't matter. This is your default LM parameters, which is maybe like very big, all right? But you can also use LoRa as a parallel layer here. Low rank adaptation, there's LoRa. And you can basically train a smaller set of network. And eventually you combine both weights together to your next layer. And your LoRa is not just one layer. Your LoRa is actually all layers, all right, or as many layers as you want. It's just a parallel branch that you can train separately. You freeze the weights of the main LM parameters, and you can train the LoRa branch separately. So, I mean, to me, I actually don't like LoRa because I find LoRa, as with the explicit memory and implicit memory kind of confusion. LoRa can cause confusion also because if your LoRa is quite different from your main LM parameters, your output will be confused. So I don't really like LoRa, but I can understand why they use the LoRa patch, because how else are you going to say that, hey, you know, change the LM parameters this way? It's going to confuse the LM if you suddenly change the LM parameters. So by using a patch to say that, okay, if I want to do this in my base model, I just update the patch. One thing is it trains faster. Another thing is it doesn't really confuse the model, but it might still cause confusion in my opinion. So this is not the best approach. The best approach is we can apply it directly to the para, okay, the LM paras itself. But I don't think this is done for MemOS, right? So I also did ask the authors, of MemOS. I asked on their Discord group. I asked them, if I use closed source LMs, how am I going to do the activation state and the parametric patch, right? Because you have no access to the models. And so they say, yeah, indeed, you can't do that. But if you use closed source LMs, you can still use the MemCube. It will just be purely based on plain text, which makes sense because everyone else is doing plain text only. But if you are using your closed source LM like DeepSeek, I guess Qwen 2.5 is open source. If you use your own open source models or Llama 4, Llama 4 is not say very good also. Yeah, but if you use the kind of models that are open source, you can actually use the activation state and parametric patch as part of the model, because you can define your own parameters like that. All right. So these are the three things. Okay, I see some chat message. Okay, yeah, no problem. Yeah, see you, James. No. All right. So the main thing is that you have these three things here. You also have a metadata that says that, hey, when was this created? When was it last used, and so on. Because this one, if you have other programs that operate on it, other programs can use this as reference to operate on the memory. So the metadata is like, if you have a packet of information, like for example, now you have your IPv4, IPv6 packet. You also need to have some metadata information to tell it like, hey, what this packet about. So this metadata header is important if you have other things that operate on this MemCube. So remember, MemCube is not static. MemCube can be changed. MemCube can be added. MemCube can be fused. MemCube can be deleted. And all these are done through external programs acting on it. Later, I'll share with you some of this. So you have also some access control, because if this becomes a marketplace in the future, if it's your own private memories, you kind of don't want other people to take it, right? So, you might want to have some password here, who has control over it. Yeah, so this is like a foundation for some ecosystem where you can trade memcubes with one another. Like eventually, if let's say we are able to just plug and play your LoRa patch into a base model, or like everyone uses the same LM next time, maybe, you can plug and play the activation state and parametric patch. But right now, if it's a different LM, you can't do this because your activations and your parametric patch are all LM based. Okay, it's different for each LM. Right? But let's say in the future when everyone use the same LM, or we figure out a way to convert things from LM to LM, like for example, we figure out a universal information that enables transfer between LM systems, then yes, this access control becomes important, because we can then move packets to one another. I can download you one packet of information to from me to you, stuff like this will become a reality. Right? You can also say that, hey, what's your kind of storage profile? How many dimensions you have? Is it compressed or not? Yeah, so this possibilities are endless. I don't want to delve too much into the details here, because to be honest, this is like V0 or V1 of it. It will change. It will change based on what is needed. Right? But the idea that you can shift your memory between the three forms is really cool. Okay, and you can have different things that can be used to retrieve your memory. You can do context aware, priority based. You can based on like, there are some other modules that like mem scheduler. After a while, maybe after 1 year, delete the memory. That kind of thing. You can have hard coded rules inside here for different programs acting on these base units. So you can treat these base units of MemCube as really just one tiny dot in an ecosystem consisting of many programs acting on it, overlapping programs, competing programs, and so on. So it will be an ecosystem, much like how a cell is regulated by a body systems. One cell regulated by chemical signals in the body, also regulated by chemical systems from outside of the body, also regulated by external factors outside of the body. There's many things that regulate it. All these things are like programs, like mem scheduler and so on. Okay, we can also, if let's say you have certain intention to modify some memory, you can adjust access rights, change the memory itself, attach a prompt to it, inject some bias, edit the black parent block, merge, and yeah, so this is very huge. The possibilities are endless. So I'm also not going to cover too much on all these external programs because, as I said, this is like V0 or V1. It will change, all right? You don't have to know all this. The main thing is that the memory can be adjusted between these three layers. And how do you do this, right? I think I have a slide for that. How do we convert between abstraction spaces? So the answer is frequency. All right, so from plain text goes to activation. The more frequently used, we convert into the activation template, right? Because we reduce the input tokens, we reduce them to like 1 or 2 embedding values. It's much easier. Activation to parametric, or also plain text to parametric, you can basically say that, hey, if let's say I keep having a knowledge that is stable and reusable, again, this defined by someone, all right? Means that this knowledge shouldn't be changing too much. Okay, because the knowledge change too much, you don't want to put into the model parameters. It will affect other tasks. If this knowledge is very stable, like for example, the tree is made up of a tree bark and leaves. All right, this is a stable fact that won't change for years. Yes, maybe I put that in my parametric in the network implicit memories so that I can, without any reference, I already have that knowledge, right? Of course, you can go the reverse. This is quite interesting. If you have something that is maybe in the LoRa parameters and you realize that this is not used much, you can put it into back to plain text form, all right? And why can you do this? Okay, this is very interesting. You can convert parameters directly to plain text. And this is so cool, all right? Because it means that if you say that, hey, the tree is not green anymore, a tree is not a tree bark and leaves anymore, maybe, oh, sorry, maybe I use something else. Python 3.7 is not the latest Python model anymore. I don't want this knowledge in my LM. I take this out from my parameter space and put it into plain text, which means that I can use retrieval augmented generation to take the plain text, but it won't affect my base output anymore. So the base output, the LM will essentially have forgotten what's Python 3.7. And that would be quite cool because, instead of having everything in the internal parameters, if you have like for example, LoRa patch kind of thing, you are able to say that, hey, now let's not use this during inference, let's not use this anymore. Okay, let's just use this. And we are able to do this because when we store the MemCube, we store in all 3 states. Unless, of course, we use a closed source LLM, then you can't convert between these 3. But let's say if you are using open source LLM, you have all 3 states stored in memory. You can say that, hey, this knowledge is outdated. Let's not put it in parametric. Let's put it in plain text. And this would go into your database. In fact, you might even say that this memory is useless. I will just delete the whole MemCube. Then you can delete the whole thing. Yeah, so it's quite flexible. Can you see the flexibility here? You are not kind of entrenched in existing knowledge anymore. Any knowledge is not sacred. You can just delete it when the need arises. And you can put in new knowledge when the need arises as well. So essentially, we moved on from a paradigm where the LM internal knowledge is sacred and unchangeable to something that, because you use a LoRa patch, you can just take out that memory from the weights. Once I take out that patch, I no longer have that memory, right? And I guess LoRa patch can be done in parallel. You can have LoRa patch 1, 2, 3, 4, 5. So you can, let's say you have 100 memories, you're going to have 100 parallel LoRa patches. Yeah, so at least this is how I envision it to work. Of course, if I say it wrongly, please someone help to correct me. Yeah. So this is going back to how memory would evolve. All right. So we go back to one of the earlier slides, and you can see that right now we are sort of at this stage 1, all right, where, okay, I mean, some people move to stage 3 already, but like most of us are stage 1. You have memory that is stored in databases and memory that is stored in database and memory stored in model. That's a kind of stage 1 memory where the LM is trained separately from your external database. Stage 2 memory, we infuse it with a bit of human inspiration, cognitive inspired memory, where we store the memory, by priority. Like maybe like you put emotions inside here, or you like encode by locations. like for example, the hippocampus, you learn how to delete memories. Okay, maybe the delete is stage 3, right? So yeah, basically how to make the memory a bit more efficient by encoding them more efficiently, inspired by humans, like how we store memory in the hippocampus, neocortex. So again, I would say that this is not full of memory. This is not the whole of memory. This is only brain-based memory. Increasingly, people also have body-based memory, out-of-body memory, and I think science is not there yet for memory research. All right, so but let's just assume human-like memory is everything there is. Then yes, we can learn from the human brain to encode the memory. Okay, then we also can learn a bit of okay, this is not really like how the human brain would do it, but we can actually add tools to do memory management. So you add memory tools to modify, add, or delete memories. So this is the next stage where you are not just a static database, you have a dynamic database that you can retrieve, you can modify the memory, you can update. So good example of this is Mem0. Mem0 actually does this. You can modify your memories in Mem0, or you can use tools like modify memory, add memory, delete memory, update memory. These can be tools given to an agent, and then this agent would be able to modify that memory accordingly with the tools. Okay, that's stage 3. And what MemOS is actually this stage 4 here. Okay, this is MemOS, and this is something that is very different. So in this MemOS, memory as a first-class citizen. So no longer do you have a differentiation between external and implicit memory. Everything is in that full range of that spectrum, and you just choose what memory you want to be activated at all times. I mean, you can even activate plain text activation and plain text activation and parameter. You can have all 3 activated at the same time. No problem. I mean, it's a spectrum, but of course, most of the time you just only want to have it at 1 because you can save the inference costs. So with MemOS, you have everything that you can do with memory management. But in addition, you have full control of your database and full control of the LLM's memories. And that's huge. Okay, that's a huge paradigm shift because we are no longer constrained by what is given to us in the language model itself. Right? So this is an example of how memory can be shifted. That's what I said earlier. Your plain text memory is explicitly stored. It's already organized like some textbook. You can encode it into activation using KV caching. All right. And this is basically, for example, if you are talking to your doctor and your doctor tells you that your doctor has the same kind of context, like you are a helpful medical doctor, you are blah, 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 blah. You can put that into KV cache. And instead of encoding 1,000 tokens of the doctor's instructions, you can just encode the KV cache. Okay. So that's activation memory. And if you cache it even further in a LoRa, you can put into parameter space, which is embedded directly into the language model's inference. Okay, so I don't really understand this example here, symptom to mechanism reasoner. I guess you can do it in any memory, right? I don't know why they put it here, but basically the idea is the parameter memory is basically how you kind of already have the knowledge without even retrieval, right? So like there's a weights and bias of your language model. Activation memory is KV cache. Plain text memory is text. Okay, in the paper it's only text, but you don't have to restrict it to text, right? And because it's just tokens here, right? So you can have text tokens, you can have image tokens, you can have video tokens, no problem. It's totally multimodal. And you can imagine that a totally multimodal system would also work for activation and parameter memory. Okay, why? Because it's just tokens, right? So how you do the embedding of your tokens doesn't really matter whether it's text tokens, image tokens, video tokens, audio tokens. It's all going to be tokens, and so your activation memory will be, the process is the same, all right? And so to parameter memory is the same. So this memory pathway right now is just text, but it will be allowable. Basically multimodal memory is perfectly capable to be stored in this system as well. And then you can change this to go back to activation memory. You can go back to this, and the reason why we are able to go back is because when we store it, we store all 3. Okay, I'm not too sure whether you can just from parameters retrieve back your activation and from activation retrieve back your text. I am not sure that you can do that. Okay, because the embedding space is a little more compressed, right, than the original space. So I don't know, maybe you could do best match of tokens and so on. But based on my understanding of MemCube, you should store all three. You should store all three at the point of encoding. Okay. Again, correct me if I'm wrong, but I think it's very hard to do the backwards path. All right. This forwards path, I understand. Backwards path, I think is difficult.
So the the data compression issue I brought up earlier, so it's perfect for going down the pipeline, like you said, because of the performance. So you don't actually lose anything. So you can go all the way down in compression and you don't lose performance. But trying to get that data back when you're trying to go back up the pipeline and invert the pipeline, what you're saying is that it makes sense that it's much more difficult because you've given away the data. There's no way to chart the data back in and sort of do your thing and try to go back the pipeline with the activations and then the decoding based on that. So
Yes, indeed. Yeah.
so I don't think there's a way to apply the rule on the inverse just because the data's already lost and you can't recover it. The only thing I could think of is maybe you try to reframe the computation in a way where you can get back your computation. I forget what the name of it is. It's a type of logic computation where you can do your computation and then you can invert it and you don't actually lose anything, but you also don't spend any energy doing it because the computation's already done and you're able to get back that computation, if that makes sense. I forget, it has a name. I've studied it because I'm fascinated by it, but I forget the name of it off the top of my head. I don't know how you'd implement it in this system because this is what I'm talking about is basic computer science theory. This is much higher level of abstraction. We're talking about like actual like LLM memory. I don't know how exactly you implement it, but I think it'd be fascinating to research.
Yeah, definitely. So I myself also agree that the backwards pathway is difficult to extract back, especially back to the main text itself. You put something in embedding memory, it's almost impossible to get back the main text. I mean, like there's so many possibilities to encode in the same embedding space. So what you said makes sense, and yeah, definitely an area of research for this. If you can get back, I'll be impressed. All right, I'll be impressed if you can get back here. Yeah. Okay, so I'll be moving on. All right, so this is MemCube. MemCube, as I said, is the stage 4 of this whole thing. You can not just have memory editing tools, you can also change the base memory. That's cool. That's so interesting, right? Like imagine you say, hey, forget about the matrix. Then LM will just forget all information about the matrix. Imagine you can do that. That is not possible right now, but if you have all your memories as a parametric patch, sure, you can do that. Yeah. So that's quite cool. So what's the MemCube content? So again, you can have description of the block's identity, what organization it came from, the timestamp so that you can delete it after a while, lifecycle modeling. You can come from whether is it user input or retrieval from external sources, or is it from your inference, like for reflection and so on. So, you can say that, hey, I only want to take memories that come from the real world, that come from my observation. And you can just filter by origin signature. So you can see this is a filtering system already. Okay, because you can filter by input type. All right. So you can also say like, oh, what is it? Is it a task prompt, fact, user preference, and so on? So this again is the structure to do retrieval for this memcube. Right. Again, we don't want everyone to access to your own personal memory, so you need to have some security here. So you can have like, access control of like where your memory should be written, read, write, or share, like whether you want to share to other people or not. Is it open source, closed source kind of memory? You can also specify, hey, destroy this after 5 seconds. Like Mission Impossible. This message will self-destruct in 5 seconds. That kind of stuff. You can specify that in your lifespan policy. You can say, hey, should this memory be exposed to the top layers for scheduling and so on, or should it just reside in the lower layers? All right. And also like maybe how do we make sure this memory can be traceable? Should we add some watermarks to it? Yeah. So again, this is quite advanced stuff because we haven't really gone to the MemOS level yet globally. This is just the start. But I quite like this idea, like you can treat memory as packets, you can send packets to one another. Very cool, very cool. I think whoever came up with this idea, or which, not whoever, but which group came up with this idea, in this case is the China researchers, they are quite far-sighted. They have seen a system that can already work. In fact, they may already have a working implementation, just that it's not shared open source yet. Right? So you also have stuff like, behavioral usage indicators, like saying that, hey, how many times has this been used? Okay, because if we have this usage characteristics, you can say, hey, this memory is only used one time in 1 year. Let's make this back to plain text. Or if you say, hey, this memory has been used 1 million times in 1 month, let's put it into parametric memory so that, your read-write costs will be lowered. So you can store this telemetry or behavioral usage indicators to, convert the memory from one type to another. So it empowers adaptive orchestration of memory. And you can also have access patterns, like saying that whether memory is hot or cold, like when was the last time it was used. So if it's used quite often, maybe you make it into fast access layers, which is parametric layers. So again, this enables you to convert the memory types from the spectrum. And that's really cool. All right, that's really cool. So these are the kind of things that are present. Right now, we've been spending our time talking on these top 3 layers, the 3 layers of memory, which corresponds to traditional, like, parametry is like the register layer, activation is the cache layer of your computer. Plain text is like the input-output buffer. All right, so this basically has some computer analogs or OS analogs. Later on, at a higher level, we can schedule memories, we can store the memories, we can, interface the memory with other things. Like we can also have a, backend driver to like preload the memory into certain systems, deploy memory as a package to other people. So they already have names for this: mem scheduler, mem vault, mem API, mem loader, mem store. I'm not going to go into details for this because, as I said, these are not too important. These are just programs that can act on the base MemCube. All right, there can be as many programs as you like. All right, these are just some examples of how you can manage your memory. Then, of course, at another layer, you have security layer. We can have authentication, we can have logging, we can have fault handling. So this corresponds to like off module system log, exception handler for your OS. So it's quite cool because you could audit like where your memory went to. You could control who has your memory. You could, if your memory is corrupted by someone else, you could, something like blockchain, I guess. You could go back at the previous instances of your memory, because I think each memory will have a history. Right? And you can basically, like GitHub, you have V1, V2, V3. You can go back the versions and get back your original memory before it's corrupted. So at least that's what I think it is. So it's very cool because instead of, let me emphasize this, instead of memory being in the LM system or like database, memory exists on its own. Memory chooses which system to belong to based on external programs. Or not say chooses, memory will have a system to belong to based on external programs, because like external programs can shift whether it's plain text or activation or parameter. And this is memory native, right? The control lies within the memory itself, not within the LM and not within the database. Yeah, this is quite mind-blowing. I mean, it's a different paradigm altogether. It's no longer LM first. It is memory first. And this memory can very likely be LM agnostic. So maybe if you have 10 LMs that you want to transfer to and fro, you might be able to, in this activation state and this parametric patch, maybe you do one per LM, then it'll be LM agnostic, because it may not even be LMs in the future, it might be something else. But the idea is your control lies in the memory unit itself, in the MemCube itself. Your control does not lie in the LM, neither does it lie in your database. It's a paradigm shift. Yeah. I haven't really seen an implementation of this yet, but the very idea of this is quite exciting, right? And this is how it looks like, when you have a memory, you can manipulate the memory here. Like for example, you have an input, my dog needs help. You go through like the memory pipeline to extract out the chunks and so on. You can, You can say, hey, I split into chunks as well. You can specify the memory pipeline to either do it manually or automatically, auto chunking and so on. Or it may not even be chunks, it might be a summary and so on. Yeah, you can specify how you want to do it. Okay. And then based on this, you can store this memory, or in this case, they are talking about how to respond to this prompt. So maybe your memory pipeline can say, or MemReader can say like, hey, extract out sources that are related to docs, or memory API. I mean, either one. Can't remember what each of them does. Let me go back and see. I think it's under memory API. You can call other memories, and then you can rack kind of thing. So rack is included inside here because you can take out other plain text memories or other memory cubes to respond. So instead of doing rack over plain text, you do rack over memcubes. Because your rack over memcubes means that you may just take the activation memory, or you may just take the parametric memory. You don't have the plain text rack, right? So this is the difference here. And after that, you have a conversation, you can maintain your conversation using stuff like scheduler, lifecycle to delete away stuff that's not relevant in your long-term conversation and so on. Yep. So, you can even store stuff like this semantic stuff. You can store it inside your memory. The user has a doc. This can be stored in long-term memory. Then, you can even say that, hey, I want to do even more stuff. I want to do stuff that is related to access control. Then you can go to infrastructure layer. You can say, hey, these memories should be private. It shouldn't be done externally. Then you can do like mem governance and so on. There's a lot more. In fact, if you want to package your entire conversation as a memory packet for someone else, you can put in the mem store and someone can download it. Yeah, so this is huge. I only talked a lot in the top few parts, but down here is huge. Okay, down here, operation and infrastructure layer is huge. I just don't want to cover it because I think these are very flexible. I mean, there's no fixed way to do it. Yeah. So this is how the memory lifecycle is. If you look at this very complicated diagram, you have a prompt, you augment your memory, you manage your lifecycle. There's so many things you can use to update your memory, right? Then you can go to the mem scheduler to see like what should the memory be used for, like where should it go. And then your encoding, you have plain text activation parametric. All right. In fact, for parametric, they even put external parametric and intrinsic parametric, which probably means the LoRa part and the non-LoRa part. All right. The extrinsic is probably the LoRa, and the intrinsic means the base memory. Yeah. So you can do both. You can use this to decode back to the prompts. Then you have one whole layer of governance or memory, and then eventually going to the mem store. It's huge. A lot of things here. In fact, if you just talk about this, you can spend 3 hours talking about it. Yeah, it's a huge thing. So you can read the paper for a succinct version of this, which is like 5 to 6 pages of how all this is done, right? But I think the main thing here is not so much the layers below. It's more like the layer of the MemCube. Because if we can wrap our heads on the idea of a MemCube being a very versatile memory that can dynamically change from plain text to activation to parameter, I think we can understand this really well, then you understand the ecosystem as well, because the ecosystem is just external programs operating on this. Yeah. So, all right. So these are the future plans for this MemCube. We have a cross LLM memory sharing where, you could interoperability and module reuse across different LLMs by sharing these memories. Some standard protocols will be defined. So I guess all this will be based on like open source LLMs because this is where it will be done best. But of course, if it's closed source LLMs, then you just share the plain text memories. All right. Self-evolving mem blocks, you can develop the memory units that can self-optimize, reconstruct, and evolve. All right, so this is really cool. I quite like this idea. Like, this means the memory itself has a mind of its own. All right, scalable memory marketplace. You can sell memories, you can buy memories from each other. So really cool, really cool. I really like the idea. But one note of caution that I have is that I've done a lot of research on memory, and I find that if you just use memory itself, you might actually cause the agents to fall into a cycle where it selects previous actions based on memory, which may not be ideal if the environment has changed. Like if let's say you have two paths here, and you have one path that is blocked and another path that is not, and you say that, hey, I always go to this path. But after a while, this blockage might be gone. And if you don't revisit that blockage, you will never know. So you need something to tell you that the memory has shifted. So you explore that area, or you do explore, exploit, So just purely relying on memory itself may be an issue. So we need to have other systems in place to break out of these negative cycles. Like you can do simulations of various actions, or you can just get knowledge from other people, which I guess is possible if you do a memory kind of store thing. You can get knowledge from other people. Or if you look at my previous videos on universal filter, you can have something like Akashic records that store memory for everyone, store memory of everyone, and then you can, if you can query with your intention, you might be able to get up-to-date memories. Okay, so we may not want to call it Akashic records if you don't like metaphysics, but the idea is you have a common global store. Okay, maybe call it global records, all right? So this is something that you might be able to use to help break out of this negative cycle of using outdated memory, right? Of course, if you have the simulation itself, you can do simulations of all the different actions, especially with like quantum computers. You might be able to simulate everything at one go. Yeah, so that is something that will be suitable in the future. So memory is very useful, but I just want to caution that just using memory itself may not be enough to be adaptable. All right. So this is just my caution. Of course, I still like this paper a lot. That's why I'm covering it. Okay, so yeah, without further ado, let us go into questions to ponder. We have 5 minutes here, so let's just cover what we can. So first one, is MemOS the same as just using memory tools? Okay, I think we have covered this just now. So using memory tools is stage 4, is stage 3. But if you have flexible memory allocation between memory spaces, that's stage 4. And of course, stage 4 includes more things. But it's more than just an agent using tools, because you can flexibly make the memory from plain text activation to parametric form. And that is beyond memory. That's beyond an agent with memory tools. Right. So next, would a unifying OS framework for memory be too bloated for most basic use cases? Yes. All right. Yes, it's too bloated. Okay. For simple use cases, this is not needed. Okay. For example, if you just want to do rec of a document that is unchanging, why bother encoding all this? Yep. So this is not that needed, because all the extra layers like the memory scheduler layer, memory API, all this will take up bandwidth and compute. So if your use case is just really just taking a static document and answering questions, a document-based rec and so on, you don't need all this, right? This is more for if you want a dynamically changing database and so on, then you can consider this framework, right? If can we implement MemOS with any LLM, including closed source ones? Yes. Okay, but closed source only can use plain text memory. Okay, this is verified with the authors of the paper already. So yes. How can memory be shared across agents with different pre-training parameters? I don't know. You need a universal information to store all memory to convert. But if you cannot have this universal information, the next best is you can have you store activations, parametric modules for most common open source LMs. That's the next best you can do, right? And each time a new open source LM is created, you can have a module that auto converts plain text into activation parametric. Because from the plain text LM, from the plain text, or I'll call it input space, like image tokens, text tokens, video tokens, audio tokens. From the input space, you should be able to convert to the embedding space or the activation space for any open source LLM, as well as the parametric space. I think all these are possible because it's just a one-way conversion. Okay, so I think once we get the hang of it, whenever you want to say, hey, I support LLM-X, immediately all your memories will go through some encoding layer, and and you get back all the parametric and activation layers. Yeah, so at least this is how I envision it. Yeah, so this is the easiest way. Of course, if we can find out a way to do a common code to talk to all LMs, then you don't have to convert to this. You can just convert to the primordial space of information. Okay, what is this? I don't know. Okay, but if let's say we can figure out something that all LLMs can be converted to, and then you can retrieve back for each LLMs, then, we perhaps could use this. Okay, so I've come to the end for these questions to ponder. You have anything else you want to raise up or discuss about? We have about 1-2 minutes.
No, I think I'm all good. That should cover it for the session.
Yeah. And thanks so much for staying true. I think this is, but you agree this is quite a major paradigm shift, right? Like it's quite different, right? This part.
Yeah, it's moving beyond the typical knowledge graphs or typical memory storage systems and kind of creating the higher level of management or abstraction for all of these different memory types.
Yeah. I really think there's a lot of potential for this MemCube idea. And the moment we can interface with different kinds of open source LLMs, like just using this MemCube, and you can exchange memory packets, change the life cycle and so on, that is really cool. And you can do retrieval over MemCubes, which you can do right now. That is really, really very cool because you can control where your memory goes. Yeah, and I think I've never seen this before. This is the first paper that I see that, encourages the shift between these three memories. So yeah, without further, in conclusion, I really like this idea, and I think there's a lot of potential for this. And we are shifting into a memory first kind of approach rather than, memory as a by the way kind of thing. So yeah, and that's the end for the session. And yeah, feel free to discuss more on my Discord and everything. And I'll see you around. Okay, bye, Brett.